I am Brian Champion, the Political Science and World Politics Librarian and Coordinator of Library Lectures. We welcome students, colleagues, and invited guests here today to this, our last House of Learning lectures for the semester. With Professor Britt's lecture today, we conclude 5 years of House of Learning lectures featuring faculty from every college on campus. Our first House of Learning lecture was Professor Donnelly Bowen on Osama bin Laden, and it was standing room only in that January 2002 lecture. Since then, topics have ranged from Professor Clayton White's study of peregrine falcons around the world to Professor Dale Pratt's discourse on the creation and impact of Cervantes' modern novel, Don Quixote, from Professor Brent Adams' colorful and imaginative display of digital animation to Professor Diane Spangler's compassionate explanation of depression and women, and much in between. We hope you have enjoyed our wide and varied offerings as much as we have enjoyed bringing them to you. As mentioned, our House of Learning lecture today features Professor Britt from the Department of Geological Sciences. His address is entitled CSI Moab, Dinosaur Death Assemblage. The library sponsors 2 main lectures and lecture series, the House of Learning Lecture Series and the Alice Louise Reynolds Women in Scholarship Lecture. Through these lectures, the library brings together scholars and students to engage in a civil discussion of ideas, and in so doing, the library contributes to building a learned community which fosters the faithful life of the mind. The House of Learning Lecture Series title is taken from the 88th section of the Doctrine and Covenants, verse 119, where the Lord instructs the saints to prepare every needful thing, even a house of learning. Because the library is the campus repository for the literature of all academic disciplines and scholarship, the library is well positioned to be considered BYU's House of Learning. The Harold B. Lee Library takes seriously its campus role as the intellectual heart of inquiry and knowledge and is honored to provide this House of Learning lecture today. Now, about today's speaker. Professor Brooks Britt from the Department of Geological Sciences earned a Bachelor of Science degree in Geology from BYU in 1982 and an MS degree also in Geology from BYU in 1987. In 1993, the University of Calgary in Canada bestowed a PhD, and subsequent to that, Professor Britt became the curator of paleontology at the Museum of Western Colorado in Grand Junction. In 1998, he became the director of Stewart Museum in Ogden, and in 2002 joined the BYU faculty. Professor Britt has authored or co-authored several articles on regional paleontology, including recent published works on the paleontology of a theropod, and I had to look this up. For those who don't know, a theropod is a 2-legged, beast-footed dinosaur, of which Tyrannosaurus rex is the most famous example. So his work on a theropod of the yellow cat family in the Cedar Mountain formations here in Utah, as well as work in the Dalton Wells and Dry Mesa quarries, the latter of which produced an interesting article on dinosaur eggs and babies. His work has focused on the pneumaticity of Archaeopteryx, an early bird form dinosaur. And you may have seen the front page story in the Herald today about new research that talks about how dinosaurs did not have to die before mammals somehow, well, we don't want to say evolved, but grew. In addition to his scholarship, many students know of his concern for them and for their academic success. He is an exemplary role model for them as a faithful scholar. It is with great pleasure we welcome today Professor Brooks Britt.
Thanks for that kind introduction, and I'm glad the dinosaurs are dead, actually. That's what the article is about, the demise of the dinosaurs and the rise of the mammals. But anyway, I'm thrilled to be here talking about dinosaurs, my favorite topic. And I love to meld dinosaurs in with geology. I work in both those areas. And bear with me for one moment here while I get the projector running then. So, this is, if I can find the right key here, we'll be rocking here. All right, this quarry that I'm going to be dealing with is near Moab, Utah. It's about 12 miles up the road from Moab on Highway 191. And it's been an interesting story. I started working on this actually when I was an undergraduate, and I was going to do a master's degree on it, but my professor had me work on something else he thought was more important at the time. So now that I'm back here, I'm back working on this project, and I'm excited to be here. So I'm going to cover a few things: where these dinosaurs were found, and how we collect them. I'm going to review how we collect these and process them and get them ready to be studied. And then we're going to look at the geology, because geology tells us about the environment in which these dinosaurs lived and died. And then we'll look at the age of these rocks that they've been recovered from, and talk about the dinosaurs themselves briefly. And then we'll look at bones. We looked at about 3,600 bones in this study to determine how these dinosaurs died or what happened to them from the time they died to the time they were fossilized. And then I'll review the sequence of events. I'll summarize it, wrap it up. First of all, so here's the locality map, and you can see there's Moab right here, and it's a 12-mile ride out here to the Dalton Wells Quarry, and located right on the margin of Arches National Park. It's spectacular. It's breathtaking scenery out there. Here's a view of the quarry when we were getting ready to open it, and you can see the La Salle Mountains in the background, and here we are scouting the surface of the hill prior to opening the quarry. Everything you see in this picture, they look like a bunch of rocks, but in fact, everything you see there practically is a bone. Unfortunately, the bones are the same color as the rocks. They've taken on the stains. But let's look at how we pull these bones out of the ground. As you all know, you've all seen movies. The paleontologist lays on his belly with a dental pick and a fine little brush and gently brushes the dust off and rock off this, right? Okay, that's partially true, but here's reality. We bring in some D9s and D7 bulldozers and we get things ready. These are gentle. We do them. We know where the bone layer is, so we're not damaging the bones. But what we were doing at this time, we'd excavated back to below the sandstone level, and these large blocks were falling down. And we thought, rather than sacrifice our students and volunteers, we'd take some of those blocks off and open a whole new area. So our tools range from these bulldozers to jackhammers to large diamond saws, and then sometimes we use a dental pick and a brush, but usually you do that in the lab. So once the bones are uncovered, then here we have the crew on a typical day in the quarry, slaving in the hot sun. And I'll show you how we get these bones out. When you find a bone, the bones are usually broken into hundreds or perhaps thousands of pieces. And you can't just lift them up and take them home. You'll never get them back together again. So what we do is we drip a consolidant, which is basically a glue that's dissolved in a solvent such as acetone. We drip that on it over a period of hours or days, let it harden up, bind the pieces together, and then we take tissue paper and we come in. We encase the bone in tissue paper, that's the wet tissue paper, and then over top of this system, we put plaster of burlap that we've soaked into burlap sheets of material and encase the bone completely, just as a physician does for when you break an arm or your leg or what have you. So this immobilizes the bone, and then we dig underneath it and then flip it over, repeat the process again, and then you pick it up and put it in the back of the truck and haul it back to the lab. But before you pull it out of the ground, before you put these plaster jackets on them, you have to record some data so that you can interpret what was going on in millions of years ago. So here then, what we do is we we simply map these. We have a grid. We divide the whole quarry up into a set of meter square grids and record the position of each bone. Furthermore, each bone then is assigned a field number, and we put down various bits of information that we'll find useful once we get back to the lab. Because in this quarry, we've pulled out a few thousand bones, and it's hard to remember what you thought about when you first pulled it out. It's important, too, to prioritize your tasks once you're back in the lab. When you're in the lab, then we have students. All of our preparation is done by students or volunteers, and they use small air-powered, I guess you'd say little mini jackhammers, whatever. They're about the size of a thick pen or pencil, and they have a carbide stylus that's driven by the air. And here you can see the rock being taken off this bone by a student. And this is the final product then. All these hundreds of pieces end up being a complete bone, or as complete a bone as possible. Most of the bones are not complete when they're preserved to start with. And then, just like in Indiana Jones movies, at the end you take and you put in your big warehouse, never to be seen again. Okay, that's not true. But you put them in here, you sort them according to taxon, or what genus it belongs to, and then you come through, and now the real work begins, and we begin analyzing the bones in terms of detailing what bone it is exactly, what genus it belongs to, and we scour the bone oftentimes with the microscope, looking for microscopic marks that tell us about what happened to it before it was buried. This is what everyone thinks is the end result of your material. Your study is a complete skeleton, and this one did come from this quarry. This is a new dinosaur. We're working on describing this right now. A team of us are working on this, and it's related to Brachiosaurus, Camarasaurus. It's in that group. And here's another one we pulled out of the quarry, and this is Gastonia. None of these came out complete. Each of these are composites of many individuals. There are no even partially complete, reasonably complete specimens in the quarry, and you'll see why as we go through this talk. We know these bones occur over a broad area, about 4,000 square meters, but of this area we've only excavated about a couple hundred square meters, and we've recovered over 4,000 bones, of which in this study that I'm going to be covering today, we've looked at 3,600 of these in detail. So once we get back to the lab, we digitize those maps. We take all of our field notes, put them into a database. We generate another table of data pertaining to information we've gleaned once it's in the lab. We have approximately 60 fields of data in here, each of these fields having multiple choices or note fields. And these tables and these databases are hooked directly to a GIS system, so we can touch on a bone and see everything we know about that bone without having to pick up the bone again. And these are the examples of some of the maps right there. So these bones stratigraphically come from a layer of rock known as the Cedar Mountain Formation. Cedar Mountain Formation, the age of it's been a bit up in the air, but we've been able to work out the actual age of the basal part of the Cedar Mountain Formation in which we work, and I'll cover that in a moment. But these beds, these bone-bearing beds of the Cedar Mountain Formation sit right on top of the Morrison Formation. The Morrison Formation, late Jurassic, you've heard of it. It has an array of dinosaurs that everyone knows about. Allosaurus, Stegosaurus, Diplodocus, Apatosaurus. So we know a lot about the dinosaurs from the late Jurassic, primarily from what we find here in North America and somewhat from what we found in Africa. And then you've all heard of Tyrannosaurus and Triceratops and the big duck-billed dinosaurs too, right? Those are from the late Cretaceous. The rocks we're working in here, though, are not from either of these well-known dinosaur eras. These rocks that we're working on here are from the early Cretaceous. And these are particularly important, and most paleontologists are focusing on the early Cretaceous right now because these tell us how the dinosaurs in the early Cretaceous evolved, from the late Jurassic, evolved into those that we know from the end of the age of the dinosaurs. So we're looking at a window of time that has not been open has not been searched for a long time. So, and we're right at the very base of this formation. Here's a geologic section, a stratigraphic section showing about 10 meters of the quarry area. Down at the bottom, the very bottom, is the Morrison Formation right down here. And we have channels that have cut down into this formation. And you'll notice here that we have one unit that shows bones, another unit that shows bones in it, another, and another. There are anywhere from 0 to 4 bone-bearing layers within this quarry at Dalton Wells. And here we can see we've mapped some of these channels out. There's the Morrison Formation down here. Here's our first unit. It has been cut out in part by Unit 2, Unit 3, and then Unit 4 overlies this, and bones occur in all of these. These rocks right here are primarily, I guess you would say, mud. They're not very well lithified. Sometimes you put water on it and just clean the bones off. Sometimes they've been indurated by calcite, and they're very difficult to remove from the bones. But these are primarily mudstones and siltstones mixed with some sand. They're very poorly sorted or unsorted. And then up above the quarry, we have these sandstone ledges that we had to use the bulldozer to remove. These are interesting because these represent stream deposits, good flowing streams here. And on the tops and bottoms of most of these beds, we find dinosaur footprints. We find insect traces, we find crayfish burrows, but mainly they're traces of crayfish and dinosaurs. So let's look in here again and zoom in on this area and look at the interpretation we've come up with. Based on a comparison of these sediments with modern sediments then, working as geologists, we look at these and we interpret the depositional environments. We determined that these sediments, most of these are deposited by streams or fluvial type systems, parts of streams. These blue horizons up here that I've shown, these represent lake margin deposits. So the area we're looking at is right on the margin of a lake, with sometimes streams coming through here. Other times, it's just a standing body of water with the dinosaurs walking along its shorelines. And furthermore, looking in detail at these sediments here, they're not normal. They're very poorly sorted. They have almost no structures to indicate the direction of water flow. They don't have ripple marks. They don't have cross beds, the things you would expect in a stream-type deposit. And what we interpret these then as we refer to them as hyperconcentrated flows or debris flows. They were like a mud flow at the time of deposition. They're very viscous, loaded with clays and silts and some sand, but most importantly, a lot of dinosaur bones. So here's a close-up of the sediments. This is what we find the dinosaur bones in. You can see some chert pebbles in there, but mainly it's clays, mud-type sized particles, and some silts. And it looks like it's just a mass with these pebbles floating in them randomly. But a closer observation reveals that we have some stains around here, and each of these iron stains surrounds a clast or a fragment of pre-existing rock that has been reworked and deposited quickly. Furthermore, all these are angular, and these are reworked bits of the Morrison Formation. As these debris flows came into this area, they ripped up the underlying formation and incorporated the Morrison Formation, and that's what made this stream-type system become very viscous, eventually just stopped flowing because it became it was choked by its own sediment that it picked up. So, what these bones are preserved in then are a stack of hyperconcentrated flows or debris flows. And Dalton Wells then gives us a rare glimpse into an unusual type of preservation in that the bones are not preserved in a regular fluvial channel, they're a stream channel, they're not preserved in a lake proper, they're preserved in these debris flows. And they rest right on the Morrison Formation. And for a number of years, this quarry was thought to be part of the Morrison Formation. It was difficult to differentiate them. You could only do that by looking at the dinosaurs that came out of here. And these sediments we look at here mark a shift, dramatic shift related to mountain building that was occurring in Nevada and western Utah at this time. So now, as in any crime scene investigation or Cretaceous scene investigation as this one is, we're going to look at when these animals died. How long have they been dead? This isn't an easy thing to do. They died millions of years ago. We know that. We know they died sometime in the early Cretaceous, but when in early Cretaceous? Normally, when you determine the age of rocks, you look for some volcanic ash beds. You need to find some igneous rocks that have crystals in them. And these crystals cooled in the magma chamber before the top of the volcano blew and spewed forth this big cloud of ash that then settled down across tens of thousands of square miles. Now, the problem here is in the Cedar Mountain Formation, we have almost no ash beds that we can recognize. So what we do is we take these sediments, we grind them up, or we pulverize them, and we look for crystals from various ash falls. And then we look for the youngest crystals we find in there. And those crystals then, after analysis, reveal the age of these rocks. And here are some of the crystals that Brent Greenhouse collected from here. And each of these crystals then, these are size of, well, they're not even the size of a grain of sand. They're about maybe the size of a grain of sand. They're very small. We pick them up under a microscope, and then we blast them with a laser, and then the material from that blast then is whisked off through a mass spectrometer where the various elements, in this case uranium and lead, are analyzed. And we look at the ratio of those two elements and specific isotopes thereof, and we come up with ages of about 124 million years for these rocks that these dinosaurs are buried in. Here's the Morrison Formation down below. We know from previous work it to be about 148 million years old or so. And these bone-bearing layers themselves come up with a similar age, 147, 146, and with the margin of error, these still are within about 148 million years old. So the rocks here seem to be Morrison in age. Well, they are because they've been reworked from down here. So we go up a little bit higher and pull off some material that doesn't have much Morrison in it. We find a peak for the Morrison Formation here at about 148, and this peak over here then, statistical analysis shows these rocks to be about 124 million years old, which puts them in the early Cretaceous at the base of the Aptian. And so now, based on this then, we can say here's how old the Morrison Formation is, 148 million years roughly, and these overlying rocks that set right on top of them are 124 million years old. We have a gap here of about 24 million years, a time of erosion and non-deposition. So this is critical. Now we can take these dinosaurs and compare them to other dinosaurs, other parts of the world of the same age, and see how things vary from one continent to another and from time to time. So having a good age is a critical point of this study. Now, the early Cretaceous world is dramatically different than it was today. Angiosperms, or flowers, had just made their appearance relatively recently. And there were things such as, we were just starting to get things like the sycamore tree, or platanus, and there were water lilies, various things like this found, not here in this formation, but in other surrounding formations and in places, particularly in China right now. Rocks of 125 million years old are revealing a spectacular wealth of early angiosperms. There are very few plants preserved in the Cedar Mountain Formation. The conditions just weren't favorable for their preservation. But as you can see from this reconstruction by Ron Blakey of North America in the early Cretaceous, we were missing a little bit of western North America, were we not? This is before the big Cretaceous seaway comes down and divides North America into two large islands. But places like California, Oregon, Washington, British Columbia, and a lot of Alaska simply did not exist yet. They had not yet been scraped off or accreted onto the continent. And looking on here, let's look at the position of Utah. Here's Utah, and we can see there's a tremendous amount of mountain building going on. We think of mountains always being eternal. Well, they're not. These mountains were just put into place at this time, and this is a function of North America moving off in this direction, and this plate, the oceanic plate, being subducted and going down here, and the compression of western North America resulted in wrinkling and folding and faulting, and these mountains then are the source. Some of these mountains off board here somewhere are the source of those volcanic ashes, the source of those zircon crystals used to get the ages. So you can see here the Atlantic is just opening up, and we can tell that the continents were still fairly well connected because in the early Cretaceous, we can jump to England, or we can jump to China, we can jump to Africa, and we can see dinosaurs are very closely related to those that we're pulling out of Utah at this time. As you go through time, the dinosaurs and the biota worldwide becomes much different. There's much more provincialism because of the breaking up of the continents. So now let's look at some of the specimens we pulled out of the quarry. It's easy to talk about the plants because we found one little bit of petrified wood that tells us nothing other than it's just a gymnosperm. It doesn't tell us anything. The EH and pH conditions were such that plants were destroyed in this environment. They were there, they were buried with the dinosaurs, but they were destroyed early on in the system. So it's probably a very basic environment. Plants are preserved best in a strongly acidic environment. We have no invertebrates in the quarry that are Cretaceous in age. All of them are from Paleozoic rocks. They've been reworked from sediments shed from these mountains off to the west. The vertebrate fauna, though, is fairly diverse. We have a number of taxa. The non-dinosaurian taxa consist of only 4 animals, and each of these is represented by only 1 or 4 bone fragments. So we have pterosaurs, the flying reptiles, which are not dinosaurs. We have a champsosaur, or neocristid, which looks like a modern gavial, though they're not related at all, and some turtles, just a few shell fragments. So we're not sampling. The fauna here does not represent a an aquatic environment. It's primarily a terrestrial environment. And here are the dinosaurs we have. We have 8 dinosaurs at least, and I've drawn up some cartoons here so you can relate to what they look like. We have 3 different types of sauropods. The one on the top is the skeleton I showed you earlier, the new macronarian dinosaur that we're working on. These are the sauropods. A brachiosaurid called Venenosaurus, and a Camarasauride. It's not Camarasaurus proper. It's a derivative of Camarasaurus, which lived 24 million years before this. So these are large, but not very large. The biggest ones we have are about 35 feet long. In reality, we'd expect them to be 60 feet long or perhaps longer, but almost all of our dinosaurs in this quarry died when they were juveniles, when they were very young, actually. Perhaps teenagers, or very young teenagers, I guess you would say. We have some theropods. We have 3 different types of theropods represented here. We have Utah raptor. We've collected about 130 elements of this dinosaur. A small theropod, poorly known, called Nedcolbertia, and an ornithomimid, just a few bones of this. And then, as far as ornithischian dinosaurs go, we have 2. Gastonia, a heavily armored dinosaur related to Ankylosaurus, and then an iguanodontid. They walked on all 4s or on just their hind legs. And this one had a sail on its back. So, breaking this down in terms of number of individuals, here's what we have, or just the numbers of bones we have. 42% of the bones we recover are from sauropods. About 30% are from theropods, the meat-eating dinosaurs, and the balance are from these ornithischian dinosaurs. So clearly, Saurischians dominated this regime at the time. And we have a minimum of at least 44 individuals we've recovered. None of them complete, mind you, but here's their distribution in terms of numbers of individuals. This new Titanosaur, or the macronarian, we have 15 individuals of it, all based on, and these counts are based on, we have about 1,200 bones or so of this one, if I remember correctly, and most of them are vertebrae and brain cases. We based our minimum count on the number of brain cases we found. I'll show you a brain case. This belongs to that new dinosaur. The skull would have been about this long, but most of the bones in a dinosaur skull, especially in sauropod skulls, are very thin, just millimeters thick. Soon after death, then, these other bones separate. They're not fused together like mammal bones are. They just fall off and are washed away. And the toughest part of the whole system is the brain case. And this is an example of the brain case. This is where the spinal cord comes out and goes down to the vertebral column. This is where the skull hooks up to the vertebral column. And looking down in here, this is where the brain would have been. We can tell it's a juvenile because the top of the brain case, which fuses up when they're still young, is missing. And this is true on almost all the brain cases we have of these. So this is one of the 15 that we found for our new macronarian. Ontogenic stages, in other words, how old are these animals when they died? Are they hatchlings, the yearlings, or what have you? Let me just look at another graph here. It just breaks this down. This chart is very revealing. You can see we have about 9% of the population are adults. And the balance of the population are subadults, meaning they're less than 80%, around 60-70% of their 60-80% of their adult size, and then the juveniles, which are smaller than that. So clearly, most of these animals died when they're very young, and this is interesting. And we'll wrap this together and talk about this a little later. Let's look at the quarry map. Here's Ken Staub making one of the maps of the quarry, and there's a fraction of the specimens down below there. And these bones, do you see any complete skeletons in there? Almost there are none. You just have fragments. You have bones, individual bones. You might have a string of vertebrae here, a string of vertebrae there, but nothing very complete. Nothing very complete at all, and furthermore, most of these bones are broken. Using the orientation of these bones, when analyzing by computer, we find that the stream flow was to the southeast at this time, and this is just one layer of the 4 layers of the bone layers in the quarry, and this is just a small fraction of the quarry here. So there are no complete dinosaurs. It's not like Jurassic Park where you get out your brush and within 5 minutes you have a complete dinosaur exposed. So we favor collecting bones that are identifiable, obviously. Even if it's just a fragment of bone that we can identify, we collect it and keep it. But we wanted to get an unbiased look at what really existed in this quarry. So we selected randomly a square meter right here, and we tried to collect all the bone fragments that were in this little area. And so here's what the results were. There's a map of that 1 square meter area, and we collected a number of bones from this. And interestingly, only a few of them were complete. Here are statistics then. We were going to do a cubic meter, but it took us a couple weeks or 10 days or so to just collect a 40 centimeter deep area, and we called that good. It was taking a lot of time, a lot of money to collect this out. Out of this hole, we recovered almost 500 bones and fragments. And that was our goal, was to look at every fragment we could find. We gave up on that after a while, though. We tried to collect everything that was 1 centimeter or larger square, and then 2 centimeters larger square. We finally settled on that because there were just too many. There would have been thousands of small fragments in this area. So most of these bones are just fragments, less than 1% complete. You can't even tell what bone they belong to. 97% of the bones are broken one way or another, and only 3% are complete. And this we consider to be representative of the quarry as a whole. Most everything is fragmented. It's badly broken. Now, we dug a trench along here to look at these. We knew we had multiple bone layers, and we took backhoes and dug a 40-meter long trench, 2 meters deep. And the purple items you see there, those are the bones. We found a few interesting things in here. We did a detailed collection of an area that was a couple meters high. We found every bone fragment in there, looking for patterns. And as you can see there, you have what are probably a couple layers. There's one here on the unconformity. You have another layer here, and then this is just a smattering of bone. You can't pick out any layers. But zooming back and look at all the data we have, these black bones show the ones we intersected as we dug this trench, and we've resolved 4 different bone layers within this horizon. So this was revolutionary, because usually you just dig down in plan view and look at bones, but we wanted to look at it in side view as well. Now, let's look at these bone fragments then. Let's look at these bones as a whole. Remember, I'm going to come back and look at each of these things and tie it back together at the end here. First of all, let's look at the sauropods. And the sauropods, if you had a complete sauropod skeleton, you would have the little bars in blue show what you expect in terms of shapes of bones in a complete skeleton. You'd have a small number of, 10% of the skeleton consists of small equidimensional blocks, rounded type bones or what have you. Flat bones account for about 30% of the skeleton, as do rod-shaped and complex bones. The complex bones being the brain case, for example, and the vertebrae. Now, our recovery rate differs from this. This yellow part of the graph represents what we actually recovered for all the sauropods from the quarry, and we have almost no block-shaped elements, a smattering of flat-shaped. The rod-shaped elements are well represented, the rod-shaped elements being limb bones primarily, and then vertebrae and brain cases are dramatically overrepresented. Let's compare and see if there's a different taphonomic or different preservational signal for the thyreophorans, the armored dinosaur Gastonia. The same general pattern holds true. Even though they have a different set of bones to start with, we still end up recovering about 80% of the bones we recover from these thyreophorans pertain to just vertebrae, basically, and brain cases. And then with Utah raptor, a representative theropod, again, we're dramatically skewed from what we would normally expect, where the complex elements are grotesquely overrepresented. So what does this mean? The reason we're looking at this then is to determine whether there's any, what acted on these bones. Were these bones carried off by scavengers, or were they acted upon by flowing water? And based on this winnowing effect that we see here then, we've determined that these bones were acted upon in a stream flow. There's no evidence not much evidence of scavenging or anything. The bones that are block-shaped, flat-shaped, and to some degree the rod-shaped bones have been removed, been flushed out of the system farther downstream, leaving behind the difficult to transport elements like the vertebrae, the brain cases, and the limb bones. Now, we continue on with this, looking at distributions of bones by shape and by taxon throughout the quarry, generating these these statistical clouds. And this is where we're using the GIS system to do some analyses. Let me show you what. Let's look by specific taxa. I'll show you a couple genera here. First, we have the IGUANODONTID, and you can see that in this section of the quarry, the bones are fairly well scattered. There's a bit of a concentration here, but they're scattered pretty much everywhere in here. Let's look now at GASTONIA, the armored dinosaur. Can you see they're concentrated in this one area of the quarry right here? In fact, we recovered parts of 7 individuals in here, and after looking at what bones we recovered, we realized the skin was still around the body cavity, and the skin had all these bony bits of armor in it, and tied the brain case to these. And so this is where we found 7 individuals scattered through here. They're not articulated, but they're held together by connective tissues. So there are some patterns then in the planar distribution, and there are some patterns in the vertical distribution as well. Working in this trench, as you see the students working right here, it looks like they're milking cows, doesn't it? But they're working in this part of the quarry right here where we found some interesting stuff. There we have parts of one individual of the theropod Utahraptor, and interestingly, some of them are complete, most of them are broken. This is a vertebra that's been broken into 2 pieces, but both pieces are right there. When we clean all this mud off it, they fit right back together again. Here's a shin bone, a tibia, and it was found lying right there, and this end is shattered. So what's going on here? What's happening? Well, these things, we think these are all of the right size bones to belong to one individual, but how do you get bones of one individual scattered over a ½ meter vertical area here? That's not normal for a quarry. They should be lying on the same surface. We think these were trampled down into the mud after the dinosaur died and was buried there. I'll come back to that in a moment here. Let's look at bone modifications. Tooth marks are rare. Tooth marks indicate scavenging or predation. You can't tell which. They're rare. They occur in only 1% of the bones. Shed teeth. Teeth that are isolated, that break off when these dinosaurs are feeding, are fairly abundant. In one area of the quarry, we found 65 shed teeth of Utahraptor. We would have expected bones like that to have been winnowed out by the fluvial system, but they weren't. So we interpret these to have been shed on site after these dinosaurs were brought in by the stream. Other dinosaurs came in and scavenged them, leaving behind their teeth that broke out as they were feeding. Now, looking at some of these bones, at least 6% of the bones have these dramatic scratch marks like these on that. What does that mean? How do these things get scratched? Furthermore, we have the bone. Many of these bones are fractured in place. Here's a bone from the hips of one of these big sauropods, and it's fractured diagonally across here. Looking closer, you can see exactly where this is the area that this piece broke out of. Clearly, this is broken right in place. It wasn't broken by stream flow. That doesn't happen. So we looked at the fracture patterns, and we realized a lot of them are oblique or longitudinal, and this tells us then that these bones were broken when they were green. And there are many breaks like this throughout this quarry. Many of these bones are highly fragmented. So we conclude, based on these scratch marks and these fragmentation bits, that these bones were trampled. And looking at detail of this, we realize the bones were trampled twice. Once at the place they originally died, they were picked up by streams, moved into this site, and then trampled yet again, as evidenced by that Utahraptor that's trampled in place. None of these bones are rounded. This means the bones were not transported by the stream very far at all. This is unusual. Most dinosaur bones you find in the stream are very well rounded. These are all sharp, angular fragments. Furthermore, these bones have burrows on them. Let's look at some of these burrows. Here's a burrow going through the matrix. Some invertebrate went through here, leaving behind a backfill trail. Here are some trails on the bones themselves. And here's some other examples of traces on bone. Can you see these burrows through here? These are about the size of your thumb or finger. These about 18 millimeters across, just eating up this bone. Here I'll highlight this and show you the fragmented area. The areas have been consumed. And let's look at some more. This is what a bone should look like. most of the bones we find there are beat up like this. And we realized later that these have been mined out by some organic process, some invertebrates. Here's another bone, fragment of bone, and you see some trails on here, and those trails consist of frass, or insect poop, I guess you would say. Here's the bone normal. Here's a bone that's been excavated by one of these channels. And if you zoom in on this, it's composed of small fragments of bone that were ingested by these invertebrates and then excreted as feces. Here's some bone fragments. These are trails on here. If we look more closely then, we can see there are paths, mandible marks on these bones. And here's some mandible marks on the bone, and here's what they look like if we just show the mandible marks, and they're in distinct patterns here. They're paired, almost always paired. What does this mean? These bones have been burrowed. 32% of the bones we recover from there have been consumed by this invertebrate, chewing out chunks of these bones. Sometimes they wear off big flat surfaces where these bones rest on the ground and these invertebrates came up from below, consuming them. So we end up with having 44% of the bones overall that show some type of trace on them relating to burrows. We have various options for insects we know that consume bone. They're moth larvae, beetle larvae, and termites. And looking at all these features, we determined that there was probably larvae of some beetles that were consuming these bones. And dramatically, sometimes a large portion of the bones. Then some of these bones are heavily weathered, and you can see these cracks. You've all seen bones out in the desert where you have fragments of the bone and they're flaking and falling apart. 39% of the bones show some evidence of weathering. Of this 39%, 60% of those are pristine. The bones are perfect, and some are flaked. It's bimodal distribution. What this tells us is that this population that we're looking at in this quarry, many died shortly before entombment. Others died 10 years or so before entombment, and not much in between. So we have 2 periods of death at least represented in this quarry. And what caused the death? Well, if we look at all these features, what this best matches is when you have a large number of the population being juveniles, all dying mainly just juveniles in this population, and rare scavenging, and they're close to a lake, we conclude that the death was probably related to a drought and multiple droughts over a period of years. This is based on comparison with studies done on modern animals in Africa, such as elephants. There was a drought back in the late 70s which killed off 5,000 head of elephants, and the vast majority of those, almost all those, were juveniles and subadults. The adults are smart enough to know how to find water, and they don't lose water as rapidly relative to because of their body mass. So we think these dinosaurs died due to drought, and they were picked up and carried in a fluvial stream that then eventually played out and ran out into this essentially dry basin, which then became a lake later. Let's look at this. The dinosaurs die. We have the bones falling apart, disarticulating. There's weathering going on. Bones are rotting. There are insects burrowing on these bones. And then we have a fluvial event that transports the smaller bones and the flat bones and the rounded bones away, leaving behind the skulls and the brain cases and the vertebrae. Then the debris flow system kicks into gear as this stream moves along slowly and chokes out before it reaches the basin itself, and these bones are dropped out in this debris flow. Then, once they're deposited here, and remember this event happened at least 4 different times, they're again burrowed and trampled, and then they become fossilized. So, the point here was then, we've been able to look at these bones in detail and come up with a scenario as to what happened to these dinosaurs that died about 124 million years ago near what is now Moab, Utah. So anyway, I've run through these conclusions. It's a very diverse bone bed. It's the most diverse early Cretaceous quarry in all the Western Hemisphere. Furthermore, things were pretty complex. It's not just a simple story. You don't have a dinosaur that died, picked up in a stream, and deposited. They died, they were trampled, they were scavenged, they were eaten by insects, they were transported, and then the same process occurred over again. But we know that these things were not transported very far because the bones are angular and sharp, any fragments are sharp, and furthermore, we're looking at a lag deposit. These are the difficult to transport elements. And so these are part of as this mountain system developed in western Utah, then the streams flowing out from here flowed off into a semi-arid basin, and the streams were didn't have sufficient water to continue to flow up and go up into what would now be the Hudson's Bay area or to the Arctic system, where that was the direction of stream flow at this time, the predominant flow. They were choked and just evaporated then in this arid basin. So those are that's the system we came up with, the ideas we came up with based on the data that was recovered by an army of students and volunteers, as well as paleontologists and geologists. So thank you for your time.